So we're back at this setup, unfortunately. I say unfortunately because I don't want to be here. But we've returned and we're now working on the summer enrichment courses that my university offers. So the way it works is that if you are a GTA, graduate teaching assistant or research assistant, in other words, the math department is paying for you to go to school and you teach, for compensation. They usually offer some sort of summer tuition. It depends on the university, obviously, but the way my university does it is that they offer these enrichment courses in the summer and they encourage you to take them. You don't have to, but it's made in such a way where you pretty much got to do it. So that's what I'm doing this summer while I'm preparing for this qualifier exam. And I get a number of comments on some of my videos asking me, how do I go about memorizing a theorem? Or what tricks do I have to commit stuff to memory? And I thought I would talk about that a little bit in this video because that's what I've been doing since I got back from campus. And here I've made a list of 52 theorems that most of these were covered by my instructor when I went through the course. I say most because some of these I don't explicitly remember him covering, like Cantor's intersection theorem, but it makes so much sense that it should be on the list because I'm pretty sure we talked about Bayer's theorem, among other things, completion theorem for metric spaces. So I tried to make something that sounded reasonable. And if I ever get that stupid measure theory series I promised I would do up and running, I haven't forgotten about it. It's just, finding the best possible time to do it is tricky. But if I am able to get that up and running soon, this is pretty much the 52 theorems that I'm going to go through when that starts. I may pick and choose some things. But anyway, let's stay focused on what I wanted to talk about, and is how to go about memorizing a theorem. I say the word memorize, even though a lot of mathematicians cringe when you use the word memorize, because, I did it too when I was in grade school and high school, where we don't like the word memorize because it kind of sends the implication that you're not really learning the material. You're just teaching your hand how to write in a certain way so that, it's like playing an instrument, right? You don't memorize the notes. You practice with your hand, and then, your hand learns it before your brain does. But I think that that's not a good way of thinking. Maybe in the very beginning, the ultimate goal, is to learn the material, understand how the theorem is proven, and then when you go through all these theorems and countless of examples and problems and doing research, reading papers, eventually it'll all start to come together. And unfortunately, when you're studying this type of mathematics, it just takes a lot of time. And, if you're a genius like Terence Tao, then you can just read something here once, like, for example, Heine-Borel theorem, and then you just know it. And so for some of these, that's true for me, and, some of these true for you probably. But if you're average like me, most of these is going to take a really long time to learn how to prove it. So the first thing I should say is you just got to sit down and write it. You just got to read the book, write down exactly what it says in the book, and teach your hand how to prove something before your brain does, because your hand will learn faster than your brain. And eventually your brain will catch up. So maybe if we pick like monotone class lemma, you sit down and write down the proof of the monotone class lemma 10 times. Just pick an arbitrary number. And then after 10 times, you set it aside and say, okay, do I remember how to do it without looking at it? And then you try and see how far you can get. And if you can finish, that's good. But then put it all away and then wait 24 hours, do other things, do the dishes, play video games, whatever it is that you like to do. And then 24 hours later say, okay, do I remember even the statement of the monotone class lemma, let alone can I prove it? And if the answer is no, then chances are you need to go back. You didn't do enough. 10 times wasn't enough. So then you do it 10 more times, and then the process just continues and continues until eventually you see the monotone class lemma in your sleep. And that sucks. That sucks because, I mean, who's got time to sit down and write down the theorem for monotone class lemma 50 plus times? You know, it's depending on how much time you have, that may not be feasible. So, but if you do a little bit every day, and you know, you organize and compartmentalize what it is that you want to do. You know, some of these, it's not that bad, like the construction of the Borel-Segmer algebra. You do that 10 times, you'll have it nailed down. But some of these are pretty nasty, like, what's a nasty one? The completion theorem, I think I mentioned that earlier. That theorem takes about like 3 pages to do. In the Kolmogorov text, he says that it's straightforward but long, and it is kind of long. I mean, it is long. Is it straightforward? Well, it makes sense when I'm writing it down, and then I put it away, and I'm like, nah, I can't even remember how to do it. I know you have to use a function. You have to define a specific function that does something cool, and that there's, you know, spaces where you look at Cauchy sequences. Anyway, yada, yada, yada. That doesn't make any difference. So the unfortunate truth is you just got to sit down and just go over the theorem over and over and over again. Don't worry about not understanding every single line as you go through it, because, I mean, yes, you do want to sit and say, okay, why does this line make sense? And then once you understand it, go to the next one. But sometimes another strategy is just brute force it. You don't think about it, you just write it all down, and then you look at it, and then you reflect on it. Say, okay, let me see if I can understand everything I wrote. Maybe you do understand it, maybe you don't, but you move on. Because you will notice, or at least, you know, I noticed that in, you know, going through all of these theorems, many of them use the same tricks, or, you know, have some trick involved in them. Like, for this one, you have Fatou's lemma. Fatou's lemma is used in the proof of the monotone convergence theorem and the dominated convergence theorem. So that kind of works out to our favor. And then what else is there? Let's see. What else could I give an example of? Well, there's Egorov's theorem, right? So Egorov's theorem is used in the proof of Lucian's theorem, but it's also used in the proof of the one underneath it. It doesn't have a name, but it's used in line 27 in that proof. It's also used in the proof of the bounded convergence theorem. So just by doing a bunch, you eventually start to see like what analysis is all about. And then, if you're lucky, after you do this for months on end, you'll sit down and say, okay, let me just pick something at random. And you go, and then maybe you pick Banach's fixed point theorem. And then you say, okay, do I remember how to prove Banach's fixed point theorem? And then it'll just come to you in some weird way. Like you'll think, and it'll usually be just like one thing, like geometric series. So when I see Banach's fixed point theorem, I think of geometric series. And then I'm able to kind of reconstruct it from there. So there are some tricks. You can't memorize every single line of a proof. I should also mention that. Like even my instructors that, you know, teach this course, they say they don't memorize every single line, but they maybe remember 1 or 2 things about the proof that helps them recreate it as they're doing it at the board. And that's kind of the goal for us grad students. Can we do that? Can we look at a problem? Because eventually, you know, it's not all about proving theorems, but when you look at problems, you kind of ask yourself, okay, do I remember the trick? Can I identify a trick that was used somewhere in the course that is applicable here? And maybe it's Egorov's theorem. Maybe it's, I don't know, the push forward a measure. Can I, you know, do some sort of change of variables to make my life a little bit easier? Can I apply dominated convergence theorem? Eventually, you just get familiar with the language, and it comes to you. So I guess in about 10 minutes, my whole message here was, if you brute force it and turn your brain off and just teach your hand, eventually your brain will catch up. And if you do a ton of these and just go through it over and over and over again, you'll start to see patterns. You'll start to understand what it's like doing analysis or algebra or whatever brand of mathematics you prefer. At least that was my experience. You know, I don't want to say that my experience will be your experience doing this stuff, but I just don't understand. I don't see any other way of honing a skill than just hours of practice. You know, that's how you learn how to ride bicycles and whatnot. Anyway, so I thought in the few more minutes that I have, I would probably pick something here that, you know, took me very little time to memorize, and something that took me a while to memorize. Again, I use the word memorize very liberally. For example, I already talked about Borel-Cantelli lemma, so I'm not going to pick that one again. I'm thinking about Banach's fixed point theorem, but I also like, where is it? Oh yeah, Vitali covering lemma, the finite version. So let's do Vitali covering lemma. The reason I like Vitali covering lemma, the finite version, is because when I read it the first time, I remember sitting in class and we did it, didn't understand it. And it's kind of embarrassing to say, because when I read it in a book, I understood it immediately. So the idea of the Vitali covering lemma, finite version, is that we have a collection of balls, and there are finitely many of them, hence the finite version. Family of balls in Rn. So this is n-dimensional space, Euclidean space. And the idea of the Vitali covering lemma is that we can find a disjoint subcollection. So k is equal to 1. We go up to some amount k of my family. And the important part is that they're disjoint, such that what? Such that the union of n equal 1 to capital N of b sub n. So I'm unioning all of these balls, and that is a subset of the union of, let me think here, 3, oh, I shouldn't have used n here, let's use d for dimension. 3 times b n k, where k is equal to 1 up to k. Let me make sure I got the statement right, because it's really easy for me to screw something like that up. So we have some family of balls, finitely many. I can find a disjoint subcollection such that the union of all these balls, so whatever that set looks like, is completely contained within the union of these balls with 3 times radius. So that's what this notation means. 3b and k means the ball b and k with 3 times the radius. And you can also, you know, make a comment here about the measure. So the measure of the union of bn, n from equal to 1 to capital N, is going to be less than or equal to 3 raised to the d power sum k equal 1 to capital K of the measure of b in k. And that just comes from countable subadditivity and the fact that in RD we have this scaling factor. We have 3 raised to the d power, which comes from properties of the Lebesgue measure. So that's just where the 3D comes from. You know, at first, if you're not familiar with Vitali's covering lemma, it's kind of confusing, like where in the world does this 3 come from? And the 3 is important because if this is a lemma that you would struggle memorizing, there's 2 things I have to say about it, and the 3 is how you go about quote-unquote memorizing this thing. Okay, but let's prove it first. So how do we prove it? We have this family, so the first thing I do is I choose Bn1 to be the ball of largest radius. which makes sense, you know. They're not like infinitely big balls where, you know, they have a radius of infinity. They're all finite, so they look like circles in R2 and spheres in R3. You get the idea. And then once we've chosen it, we are going to remove it, and all balls intersecting it non-trivially, which means they share points, right? And I remove those balls from my family. So maybe I'll give this family a name. I'll call it Fancy B. And I do apologize for my handwriting. I don't know why my hands are so shaky right now, but they're really bad shaking right now. Okay, so we've chosen B1, or BN1. We removed it and all balls that touch it. And then you just repeat the same argument. So we choose BN2 to be the ball of largest radius of what remains. Remove it, and all balls, I'll just write touching it. Yeah, this isn't the most mathy of words, but you get the idea. This is how you learn, in my opinion. I would not write this on a test. I would write it more formally. But as long as you understand what's going on, that is for studying purposes, that's the most important thing. So remove it and all balls touching it from the family. I always preferred the word family over collection. Well, the thing is, it's a set, right? It's a set of sets. And mathematicians find that awkward sometimes to say the set of sets. So they'll usually say a collection of sets or a family of sets. And I like to say family of sets because it sounds more wholesome, I guess. So this is the idea. And then you proceed by induction. You choose B and K. So I'll write inductively. Choose B and K, ball of largest radius. Remove it, and any ball touching it. Eventually, you run out. You run out of balls. Eventually, you will run out of balls because it's finite, right? We assume that we had finitely many balls. So this is what's called, I believe, I've heard it called this way before, the greedy algorithm, because I guess the greedy part comes from the process where you remove the ball and anything that touches it. So you continue this process and then you consider the family B and K, where K is equal to 1, and then however many there are. So say you chose K balls. I mean, you know K exists, right? Because you ran out. Eventually you run out. So we chose K balls, for example. I don't really have to write that part, but whatever. So we considered this set. And then the idea is that this family is the one that I'm interested in here. So maybe I call it B prime or something. And then it's fairly obvious at this point that the union of the balls from 1 to n is contained in the union of 3 times the ball B and K, where K is equal to 1 to K. And then for this last part here, I was going to say I'm going to leave it to the viewer as an exercise, but I figured that people would get mad at me if I do that. So we have n equal 1 to n, and if that's a subset, then we know by monotonicity, then we have measure union 3 B and K from 1 to capital K, and by monotonicity we have, or not monotonicity, countable subadditivity, the measure of 3 B and K from 1 to k. And then, using property of Lebesgue measure, we can pull out the 3D. So you have 3D sum measure b and k. And the only thing left here to explain is where the 3 comes from. So, and it comes from the way that we remove the balls from the set. So let's say that this was our b and k that we chose. So here is the ball, b and k. So it has some radius, which looks like this. So I'll just call it r. Maybe I'll call it rk to let us know that it's rk. And now I consider a ball that's 3 times the radius. So I go out 1 radius here, and then I go out another radius here. And now I consider the concentric ball with 3 times the radius, which looks like that. So I'll write 3b and k. And so I removed this when I considered my construction of b prime. And I asked myself, like, okay, so if I remove a ball and then it touches it non-trivially, then I know that this ball, if it exists, removed. This ball is removed. Maybe this ball, it gets removed. But then you have to consider the worst case scenario. So what's the worst case scenario? So best case scenario is the ball is contained inside, right? That's kind of nice because the whole ball covers it. If you have something like this, then, some of it's outside, so you need to pick a radius big enough so that this ball here gets covered. So the worst case scenario would be if we had a ball that was identically in size to b and k, and it just barely touches it. That's the absolute worst case. So that would look something like this. So this ball is exactly the same size, meaning it has the same radius. And we have to say, okay, we need to cover this guy. Well, this is still radius rk. And then what's the radius of this? It's still rk. But, it just barely touches at this point. So it must have a diameter of 2 times rk. And that's where the 3 comes from. You have these 3 radii here. So if I want to be able to cover this ball that I removed because he just barely touches and he's just as big, then I need to go out 3 radii this way and then put my big ball around it that way. So that is more or less the Vitali covering lemma, the finite case. It's the easiest covering lemma to prove. It doesn't have too much going for it. And it's used in the proof of the Hardy-Littlewood maximal function, or excuse me, the weak type bound that's used in, that talks about the bound for the Hardy-Littlewood maximal function. So that's why it's an important lemma. How do I go about remembering this theorem? I only really remember 2 things. And to be honest, this was one of those theorems where I read once and it made just so much sense. Unfortunately, Egorov's, did not. So I remember 2 things. The first thing is the greedy algorithm. This is how I get my sets b and k. So that part comes up here. That's the first part I did. The second thing is the picture. If you can remember these 2 things, then you don't even have to worry about each individual line. The whole theorem or lemma comes to me immediately if I have those 2 things. For Egorov's, it's a little bit more involved. The Borel-Cantelli lemma, helped a lot in helping me, learn that thing. Unfortunately, I don't really have much time to talk about it, so maybe in the next video I'll cover Egorov's theorem and what I use to memorize it. But I would want to do, that for pretty much all of these theorems here. I've done a pretty good job at memorizing most of them. But some of them, like Rademacher's theorem, that just scares me. That's going to take way too long. I hope he doesn't do anything with it. But anyway, it's been 25 minutes. I hope you found this video informative. I hope that it helps you memorize your theorems or whatever it is you're studying. Unfortunately, these theorems it just takes a long time. You just got to sit down and do it until eventually you know it and do practice problems. So anyway, I hope this helped.